This was the maths from 2014, just going to do the first 10 multiple choice questions as I usually do in this section. I'll do the other parts at some later time. So rearrange this to make this. You want to get used to kind of factorizing this without making a substitution just because it's quicker. So that this looks like x squared minus 8x minus 9, which means we can factorize that just with x squareds in it instead. So factorize to x minus 9x plus 1, and we can just use x squareds in there instead to make these x's here. Again, just slightly quicker than using a substitution. So now our critical values are either when this is 0 or when this is 0, but of course this can't be 0 because you're looking for x squared as minus 1. This can be at x is plus or minus 3. And so we have two solutions here, which means this quartic graph looks a bit like, well, it has two solutions, minus 3 and 3 are the roots. It has its quartic, so it goes up here, and it has a y-intercept of minus 9. So it looks a bit like a quadratic, but it will bend somewhere in the middle. I don't know exactly where. I just did this for fun. It will bend somewhere in the middle. But the key points here is that for that graph to be under 0, to be below the x-axis, we need to be in between the critical values of minus 3 and 3, and we have our answer. Just getting used to this kind of thing, doing it without substitution just because it's quicker, is probably worth it. So yeah. Number 2, so again, just like before actually, thinking about roots. So when you're picking which graph is which, intersects with axis is a good start. So let's see what happens when y is 0. Where are the roots here? So we set y to be 0, and of course now for this to work we need this input into the log to be 1. Log to base anything of 1 is 0 because 10 to the power 0 is 1. So we need this to be 1, which we solve by taking away 1 and then factorize to get two roots in the same place at just x equals 1. So we're looking for a graph that just has a repeated root at x equals 1, and very quickly we see this is the only answer, which is good because that was not very much work. C, so it has a turning point, so we're immediately going to differentiate. Good, done. Which is a minimum when x equals 1. So okay, dy by dx is 0 because it's a turning point when x equals 1. So we put in that information, we put in this and this, and we get this. Unfortunately though, 3k minus 2k minus k, and then minus 2 plus 2 is all 0. So that doesn't actually tell us anything. It has a turning point for any value of k, which is kind of interesting. So what else do we do? Well, we look at the minimum information. That means if we differentiate again, so find d2y by dx squared, so differentiate again, for a minimum, this thing is greater than 0 at x equals 1. Right, that's when a minimum happens. So we say this thing here is greater than 0 when x is 1, so substitute x is 1 in, you get this, it's greater than 0, you rearrange, and you get k is greater than a half. So that was quite an interesting question, I quite liked that one. D is quite a cool question as well. You know what R2 Drew 2 does, he sketches stuff. So okay, we've got the point 1, 0, and we've got some line y equals mx. I'm just going to choose m to be 1 to start with. And then it's very clear that this point reflects to the point 0, 1. And now what I'm going to say is, if I substitute m is 1 into these, I should get 0, 1. And if I don't, they can't be the correct answer. So okay, let's just substitute m into these. Here we get 2 over 0, which is not 0. And so this is just not going to work. This is 1 here, which means this doesn't match with this, so this doesn't work. This does, because 1 minus 1 is 0, and then this is a 1. This does as well if you check it, and so does this. But I got rid of 2 of them, so that's good. And now I'm going to try m as minus 1, because that seems like the next most obvious line to pick. And now this goes over to here, which is at 0 minus 1. And again, substitute m as minus 1 into these, and see if that makes any of these go away. Well, if you put in minus 1 to here, you get 1 minus 1. Well, sorry, which does work. If you put m into here, 1 minus minus 1 is 2. And we're looking for 0. So that one breaks down, and we're just left with these 2 here. So okay, how do I decide? So these two both work for both these inputs, if I'm not mistaken. So how do I decide which one it is between these two? Well, what I decided to do was, what if I made m really, really big? Really big. What happens to this line? Well, it becomes more and more vertical, doesn't it? Like as the gradient becomes bigger and bigger, this line becomes more and more vertical. And so as m tends towards infinity, this line will tend towards the y-axis, and this point will tend towards the reflection, minus 1, 0. So if I put m as a really big number into these, I should get minus 1, 0. The problem is, when I put m as really big into here, I get 1 minus a massive number, which is just negative a massive number, not negative 1. And so this doesn't work either. Also, the y-coordinate is broken as well. But this one does work. As m tends to infinity, this tends to minus 1, and this tends to 0, which is good. So D is the answer, I think. Quite a nice question. Did it in a weird way, but I quite liked it. Okay, this one, I'm just going to consider what happens to this thing in the bracket first. So of course I can replace the sine squared with the 1 minus cos squared and expand out, and consider this quadratic. I'm going to complete the square to find its turning point by factorizing out a minus 4 just from the first two terms. I always like to leave the last term alone. Then I'll complete the square on this thing here. Now again, if you're a little bit unhappy doing this without a substitution, make a substitution and then do it on that and then put it back in. I've done lots of this before, so I'm happy just to halve this down to a minus a half and then put it in a bracket with a square and then take away minus half squared, which is minus a quarter. I'm just happy to do that. If you want to use a substitution, do so. And then I'm going to expand out the 4. This obviously cancels with this, the minus cancels as well to make a plus 1, and then the plus 5 joins it to make a plus 6. So I have this completed the square form. Now, of course, that whole thing is being squared at the end. So what I can think about is, how do I make this as big as possible? Or how do I make it as small as possible in terms of a negative? Because if this was a massive negative in here, that would square to a big positive. So that would be the largest value. So, okay, well, the standard thing to do would be to set this whole thing to be 0 and say, well, I can get a 6 out of that easily. So the largest positive thing, because this is an upside down quadratic, right, because of this minus here, the largest positive value that this function can take is 6. That's when cos is a half, right? And this all ends up being 0, and we just get 6, which then squares to make 36, which is an answer. But the problem is, can't you just make this thing really negative, and then add 6 to it, and still be it big and negative, and then that will square to be big and positive? Like, why can't we do that? Well, the problem is that cos itself is restricted. Because cos is restricted between minus 1 and 1, the smallest I can make this thing is using cos is minus 1 to make the bracket minus 3 over 2, which will then square to make 9 over 4, which cancels with that 4, which makes a minus 9, plus 6 to make minus 3, which squares out to be plus 9, which is smaller than the 36 we saw before. So because cos is restricted in this way, just bouncing between minus 1 and 1, this can't actually matter. It never makes the value any bigger than if you just made it 0, which is kind of interesting. So yeah, 36 is therefore the largest we can do, as said. Okay, cool. F. So we start out with an x, and if we put it through the s function, we just add 1. So we can keep doing that. We just add 1 again, add 1 again. We can keep doing that as long as we want. When we put it through the t function, we times the entire function by minus 1. Right. So we just take t of this whole thing. T of x plus 3 gives you minus x minus 3, right? So this is the input, x plus 3. The whole thing gets times by negative 1 to give you negative x, negative 3 is what's going on there. You don't just times the x, because this is the entire function you're doing. You take the negative of the whole thing that you've got. So okay, how can we get to this function here? Well, the obvious thing to do is you could just apply t straight away to give you minus x, and then you can just apply s 8 times to do minus x plus 1, minus x plus 2, minus x plus 3, and so on until minus x plus 8, which is the same as this, of course. So, okay, t is 1. Using t once and s 8 times is certainly a sufficient way, stealing words from Tamura, a sufficient way to arrive at this. But the thing is, you could apply t 3 times to start with, couldn't you? Because that will get you back to minus 8, because these two are kind of wasted. They're just swapping it back again. And then you could apply s 8 times, and you get to this. So it's not necessary that this is happening. So that definitely isn't necessary, again, to use a Tamura word. So we can't deduce this is definitely the case. This is also definitely not the case, this one here, because we've got a case where s is 8 and t is 1 works, which is the opposite of this. So that's definitely not the case. Likewise here, t is 1 is a power of 2, and so is s is 8. But t is 3 isn't. So this doesn't have to be true, because t is 3, s is 8 works as well. So the answer is either this or this. Can we deduce that s has to be even and t has to be odd? Well, t having to be odd is, I think, fairly easy to conclude, because we need to get a minus x here. And every time you apply t, you go from x to minus x. And so you've got to apply it an odd number of times. Since you're starting with x, you've got to apply it an odd number of times to get to a minus x. Any more times, and is fine, as long as you do it an even number of times more after the first one you did to get back to minus x, so an odd number in total. So I think t should be odd. Now what about s being even? Well, obviously we need to get 8 times, we need to use s 8 times to get to a plus 8. The problem is, if you use a t here, for instance, to get this, you've jumped down to minus 1, and now you need to apply s how many more times? Well, 2 more times will get you back to that plus 1 situation we were in, and then we can do it as if we were going from the start. So essentially, every time we apply t, whatever number we have here flips to the negative axis, but then it takes an even number of times to get it back to where it was, right? Like 3 flips to negative 3, but then it takes 6 times to get it back to where it was. And since you need to make 8 movements kind of originally from 0 to 8, and any flip minus 3 requires an even number to get it back to where you want it to be, I think that's going to be an even number in total. So that's a very wishy-washy argument, but I think we can conclude S must be even, T must be odd. G, so this is a really interesting question. You don't want to do a trinomial. This is 3 numbers, right? Trinomial. Do a binomial. So group up 2 of these things. I chose to group up the first 2. I don't know whether this is the easiest thing to do. But anyway, now we do binomial expansion. So the first one is just this n times, so that's the power n. Then we do this n minus 1 times, this once, n choose 1 at the start. N choose 1 is just n, of course. And then we'll do this twice, this n minus 2 times, and then minus n choose 2 at the start. If you're not happy with these choose functions, I've got videos on the channel that explain these a bit more. And then you keep going. Now the thing is, this one here makes a y to the 6 term. And we need y to the 5s. And there are no negative terms in here. Because if n is a positive integer, this will stop. When you reach 0, it won't keep going like it does with fractional. So if you've done fractional, if you haven't, ignore me. So this is completely pointless, right? We're not going to get y to the 5 terms out of this because there's a y to the 6 just here multiplying everything. Now here, there is a y to the 4 term, so I'd want a y1 term here. But think about how this thing here itself expands, because of course this is in itself another binomial expansion, isn't it? And think about how this kind of thing expands. You're going to get 1 to the power m. Then you're going to get m choose 1 with this. I'm being really lazy because, of course, when you've got a 1 here, it's super easy because you don't need to write the 1s because 1 to the power anything is just 1. So you just increase this power gradually, and you just have m choose 1, m choose 2, m choose 3, and so on. But the thing is, these x and y's come in perfect pairs. It's xy, x squared, x cubed, y cubed. And so when you expand this object and this object here as well, you're just going to get symmetrical xy stuff. xy, xy squared, x squared, y squared, x cubed, y cubed, and so on. And so if you've got y to the 4 here, you only need 1 more y, which is only, so from here you need 1 more y, but you're only going to bring with that 1x. Right? And so here, the best you can do is get an x, y to the 5. So just make sure you understand what I've just said there. Here's a y to the 4. You can only get x, y's together here. So the best you can do is an x, y to the 5 in total here. Or an x cubed, y cubed from here with a y to the 4 here to make x cubed, y to the 7. Neither of which are the thing you're looking for. So this is pointless. We can't use this. But we can use this because this brings y squareds. This can bring an x cubed, y cubed from this expansion here. And so y squared times x cubed, y cubed will give you x cubed, y to the 5. So this is the term that we're interested in. Likewise, this one is not relevant because it's not going to create this imbalance here. So this is the one we're interested in. And now, of course, I've put this in blue because that's this expansion with m being written as n minus 1. So just take this and replace m with n minus 1, which is what I've done here. And now, which of this are we actually interested in? Well, that's just a constant n, so I'm going to need that. And I want this term here with the y squareds. As said, y squared times x cubed, y cubed is x cubed, y to the 5. So I just want this, this, and this. None of the other stuff is relevant to me. I just want this times this times this. That's what I want. And that's going to give me the correct x, y coefficient powers that I want here. So now I'm looking at this statement here. And I'm unfortunately, this is where lots of people like multiple choice. I don't, because if this wasn't multiple choice, I could just leave my answer here. But now I have to go through extra effort to make it look like one of their answers. So okay, well the choose function is defined to be this. Again, explained in a video elsewhere on the channel if you want to, if you're not so confident on that. N choose 1 is just n. You can see that through this formula if you think about it for a second. And now this, just replace n with n minus 1 here, and the 3 with the k. So n minus 1 minus 3 here to make n minus 4. Of course, this n times n minus 1 factorial is just n factorial, because you can introduce this n into this to make it n factorial. And now this is close to being of this form, but these two numbers don't match. So how can we make them match? Well, we can use the same trick we did here. To turn this n minus 1 into an n factorial, we just introduce the missing thing. So why don't we times this by 4 over 4, and I only did this because I saw the answer here. times it by 4 over 4, put that 4 into there to make 4 factorial, leave that 4 out, and this here is just n choose 4 by the definition here. And so we have our answer there. Kind of an interesting question. I really liked it actually, because I like binomial expansion questions. This question is also quite interesting. When you see a question like this, you should probably just try a bunch of stuff until you get a feel for the problem. That's exactly what I did. So when n is 2, 2 divides 2 and 3 doesn't. So we're following this rule here. So we say f of 2 is f of 1 plus 2. Now f of 1 is 0, so that just equals 2. When n is 3, we follow this rule. 3 divides 3, but 2 doesn't. So we follow this rule, so we do f of 3 equals f of 2 this time, plus 3, which is 5. And we keep going. When n is 4, that's back to this rule, right? So we do the previous one plus 2, 5 plus 2 is 7. n is 5, neither 2 or 3 divide, and we just choose what we had before, so that's just going to be 7 again. 6 both divide, so we follow this rule where we add 4. So we take the previous one and we add 4, and we get 11. And now I was thinking at this point, oh, all of these are prime, that's quite cool. Maybe the answer is just prime. Maybe I'm supposed to notice that. Then you just keep going for a second though. 7 follows this rule, right? Because it's either of them, so it's going to be 11. And then 8 follows this rule, because 2 does but 3 doesn't. So you add 2 to this to make 13. And I kept going because I still didn't understand the problem. I kept going all the way to 9 when I finally realized I wasn't getting prime numbers every time. So I blew that idea out of the water. But then I realized, okay, think about what I've done here to get to n is 9. Every time I've passed a multiple of 2, and strictly a multiple of 2, I've added 2. Every time I've passed a multiple of 3, and strictly a multiple of 3, I've added 3. And every time I've passed a multiple of both, I've added 4. And when they're neither, I've just done nothing. So that's kind of interesting. So what we can say is, to get to 9, 9 passes 1, 2, 3 strict multiples of 2. So I add 6 in total to pass those ones. It passes 2 strict multiples of 3. Strict meaning not also a 2. That's just a made-up word that I'm using. So we add 6. So we've got 6 from the 2s, 6 from the 3s, which is 12 in total, and one number was 4. So 6 plus 6 plus 4 is 16, and that's how we got to 16. So what I can say is, to get all the way to 6,000, I just need to count how many strict multiples of 2, so therefore multiples of 2 but not 3, I pass, and add 2 every time I do so. Count how many multiples of 3 I pass that are multiples of 2, and add 3 every time I do so. Count how many multiples of both I pass, add 4 every time I do so, and then ignore anything that's not either. And this is much easier than it sounds, right? So this is just me summarizing my results. To get to 6,000, you pass 3,000 multiples of 2, right? Because every half number is a multiple of 2, or every second number, I should say. But 1,000 of those are also multiples of 3, right? Because a third of these are going to be multiples of 3. So there are going to be 2,000 in total, 2,000 strict multiples of 2. So 2,000 times I'll add 2. So that's going to be 2,000 times 2. But also, I've just said there are going to be 1,000 that are multiples of both 2 and 3. So I may as well add those 1,000 lots of 4, because I add 4 every time I do that. There. And then I make 4,000 plus 4,000 is 8,000. And now how many multiples of 3 do I pass? Well, 6,000 divided by 3 is 2,000, but we've already said 1,000 of those are already multiples of 2, so we've already counted those. So I just need to count the 1,000 missing. 1,000 times 3 is 3,000. Add these two results up to get 11,000. I was pretty worried that I had done something wrong, because there are always these edge cases, aren't there, where I may have counted the first number twice or the last number or whatever. But because there are no answers anywhere near 11,000, I can just underline this. I'd be really worried if an answer was 11,002, for instance, and I'd be worried about whether or not I counted 6,000 or something like that. But don't need to be concerned about that because there's nothing around it. So that's quite a cool question as well. This was full of interesting. So next question then, we've got a function y equals 2 to the x to the 2, and we're going to try and turn it into this function here. Now we've got all these function transformations here. Stretch parallel to the y-axis when you put a number in front. Translation parallel to the y-axis when you add a number at the end. Translation parallel to the x-axis when you add a number in the bracket. We should know all these. Translation parallel to the x we've done. Stretch parallel to the x, that's when you put a number inside the bracket here, and then reflection in y is when you do that. So okay, how do we turn this thing into this thing then? Well, I notice there's an x minus 4 here. So if I took 2 away from the x bit here, so looking at f of x minus 2, I could then expand this out to get an x squared minus 4x, and then plus 4 at the end, which is almost this. It's really close, but it's not quite, doesn't quite work. So okay, we'll just need to fix that then. How do we reduce this by 1? It's something just to take away 1 from the function, but of course that's just all of this take away 1, so that doesn't quite work. So what else are we going to do? Well, look at the answers for inspiration, right? I've translated parallel to the x-axis first, so that's one of these 3 things. Which one of these would then help me? Right, reflection in the y-axis, changing this for a minus x. Would that help? Well, no, all that would do is change this to a plus 4x, that doesn't help. But here, stretch parallel to the y-axis, putting a number in front of the function. Would that work? And it's really sneaky, but if you stretch it with a factor of a half, and of course half is the same as 2 to the power minus 1. Because you've now got the same base, you can do this plus this, and of course this just makes 4 minus 1 is 3, and we have our answer. So we're going to translate it parallel to the x-axis, and then we're going to stretch it parallel to the y-axis. Quite a sneaky question, but also quite an interesting one as well. Yeah. I've done quite a lot of math questions, and I've never been completely stuck before. But this question, unfortunately, I was completely stuck. I'm going to show you what I did first, and then I'll have to pick up from where the work solutions went to help me out from there. But what I said was, okay, I've never seen a question like this before. Hands in the air. I've done a lot of maths in my life, never seen a question like this before. So I really had to put my thinking cap on. What's nice about fx and f minus x is there's one number that I know those are the same for. So I thought, okay, what happens if just x is 0? Because f of 0 is the same as f of minus 0. And of course this just makes 0, so this all goes away. And I get this. And I thought that might be quite helpful. And then I thought, okay, well what happens if you just put x is 1 in? You get 6 plus f of 1, 2f of minus 1 plus 3, lots of, and I'm going to call this whole integral just x. Now notice how this whole integral is just a number. Because when you integrate f of t dt, you get some function, which you then put in the numbers 1 and minus 1 for, so you're going to get a number out of that, because it's a definite integral. So that's just a constant, which I'll call x. And also notice how this is what I'm looking for. X is what I'm looking for, isn't it? Because despite the fact that I'm looking for this thing here, which you might argue is different to this thing here, it's not. Because this, when you have 2 letters like this is called a dummy variable. Again, because this is just a constant, when you integrate this with respect to t, you're going to get some function. Then when you put 1 and minus 1 in, it doesn't matter what letters you're replacing when you substitute these values in, because you're just substituting them in, you're just going to get a number. So it doesn't matter what the letter here is, this is called a dummy variable, this is going to equal this. And again, it really doesn't matter. You can be Taylor Swift if it wants to be. You can use any letter you want here. It's just a dummy variable because of the definite integral. So I'm looking for x, I'm just going to call this x. And what I also did was I said, okay, well I can make a similar equation if I use x as minus 1, because now I'm just going to minus 1 here and a plus 1 there. And that's kind of cool. I can take these 2 things away to eliminate x, which isn't great because x is the thing that I'm looking for, because I've defined x to be the thing that I want. But okay, if I take this away from this, the 6's cancel, I get this minus this equals this minus that. But now I add f of 1 to both sides and add 2f of minus 1 to both sides, I guess, or whatever I did. I think I added this to both sides as well. And you get this, divide by 3 and you get this. And that's quite interesting, that f of 1 equals f of minus 1. And also, the 1's here did nothing. So if I just set x to be y and x to be minus y, exactly the same maths will come apart. And I worked out that this function is an even function. Right? It's symmetrical around the y-axis. Any positive inputs equal the same as their negative counterparts. And I thought I had made real progress there, but unfortunately that's all I found. I tried substituting in some other values to make some simultaneous equations to solve for x, couldn't do it, just wasn't working. I had to give up. Look at the work solutions. This is basically the only useful thing that I found out. This is completely pointless as far as I can tell. What you need to do, and I'll remember this trick for the rest of the time, this is why we practice, isn't it? To learn new tricks that we'll remember. But the trick is to integrate everything. Integrate everything between minus 1 and 1. Because the idea is not to try and solve this directly, which is what I was trying to do, call it x and try and solve it directly, but to create this by integrating this between 1 and minus 1, because you've got the thing that you want there. So you can integrate the whole thing. So 6 integrated is 6x. And of course, when you're adding things, you can integrate separately. So 6 integrated is 6x, and it's evaluated between 1 and minus 1. because that's what they want. So I've integrated every term separately and evaluated between -1 and -1. Now the integral of that between 1 and -1 is just defined to be this, of course, which is good because that's the thing I'm looking for. The integral of this, or is f of minus x, so that's fine, integrated between 1 and -1 and 2. And now this is the tricky bit, but again, this is just a constant. It's really tempting to think, oh, you're doing the integral of an integral. No, this is just a constant, isn't it? Because it's a definite integral. So I can just say this is 3 times this number times x squared, and then just ignore the constant bit and integrate x squared. I've also replaced these with x's again because they're dummy variables anyway. So now I'm just integrating the x squared to make x cubed over 3 between 1 and -1. And now substitute in these things here, leave everything else alone except for this, which I can say is just f of x, because, and this is where an entire page of work actually paid off. That bit did help me. I meant I could do that. This is just 1 cubed over 3 minus -1 over 3, because -1 cubes to -1. And likewise here, 6 times 1 is 6, minus -6 makes 12. But I've already called this x, this is just 2x, and this is just 3x. The 3's cancel here to make 2x in total, and I think I end up with this statement here. Spoiler there, shouldn't have come up yet. So 12 plus x equals 2x plus, and then 3's cancel to make 2x. This is very easy to solve, and you get x is 4, or the integral is 4. That's just a really, really nice trick that is probably well worth bearing in mind. I haven't seen it before. Maybe I have many years ago, but I'll try and bear it in mind. This is why we practice, isn't it? To learn tricks like these. But anyway, I'll see you next time.